Alright, so today we'll be going through the AP Chem curriculum as quick as I can. So I know the AP Chem test is coming up for 2024. It's in a couple of days, so I'm gonna try to get through the curriculum as fast as I can. And the reason why I'm doing this is because for me at least, AP Chem it's difficult for a lot of people, but there's a kind of these tips and tricks that I learned to kind of get through the course easier, to kind of learn everything faster, and not have to memorize everything. So I just wanted to share some of those in a comprehensive summary of pretty much every unit. And so today I'm gonna try to get through Unit One, and basically we'll be covering atomic structures and properties. I'm gonna try to get through this in like a cram kind of situation where you don't have to like relearn everything. All the things you kind of need to know is what a mole is, what a molar mass for. I'm looking at 1.1, which is moles and molar mass. A mole, remember, is just a number given to how many atoms is inside that unit. It's like a unit. It's literally just a unit, right? It's like a kilograms, grams type of situation. It's basically a mole is 6.022 times 10 to the 23rd atoms, because an atom is so small that they needed another unit to account for how many grams there are in a mole, because then it would be super small number if it was just one atom, so they use a mole instead. So the number you need to know is 6.022 times 10 to the 23rd, which I think is on the formula sheet, so you don't really need to know that. And then it's also converting from grams to moles, which is just, if you think about it, if you're given like 5.38 grams of, say, C6H12O6, and you're trying to convert it to moles, well, how many grams are in a mole? You just divide it by 180, because there's 180 grams inside 1 mole of uh, C6H12O6, and that would equal to 0.02989 moles of that. It's pretty obvious, right? 180 grams inside a mole, you're just converting it, right? That's stoichiometry. Um, and then molar mass of 1 gram of a substance, or 1 gram of a element, is just how many grams is 1 mole of that, which is the molar mass. And then if you're trying to find the molar mass of an element, it's just same thing, right? It's pretty. Oh, not that. It's pretty given. If you're saying we're gonna use the same thing from before. C6H12O6. Well, if 1 mole of carbon is 12, 1 mole of hydrogen is 1 mole of oxygen is 16. I'm just not going to bother using all of the decimals. Well, there's 12 carbon atoms, so you multiply by 6 plus 12 oxygen atoms, multiply it by 12 plus 6 oxygen atoms, you multiply it by 6, and you get 180 grams per mole with C6H12O6. So I don't think those should make sense to you. It's not really something you memorize. Um, so a lot of these, like if you're given how many hydrogen molecules are, say, in um, like H2O2, right? How many hydrogen atoms are in like 1 mole of this? I don't want to make the math too hard. Well, 1 mole of 1 mole of H atom is 6.02 times 10 to the 23rd. So then, if there's 2 moles of hydrogen atoms inside water, then you just multiply it by 2, which is, for doing it, 1.204. Is that right? Oh, that's right. Be embarrassing if it isn't. Right. So yeah. Next one. Mass spectroscopy of elements. This is 1.2. Uh-oh. How do I reset this? Running out of space. So this one, all you kind of need to know is some definitions, right? Basically, an isotope is same number of protons, different number of neutrons. It'll change the stability of the element. So basically, the element will stay the same. It just has a different amount of neutrons, which it'll change the mass, right? Because if we go back to review, one electron has insignificant mass, one proton, one neutron has 1 AMU each, right? So then, if you're changing the amount of neutrons, you're changing the mass of it. And to know that, you just need, or the only thing you kind of need to know, I think, for this one is relative abundance. Relative abundance. It's basically, you're trying to find the average atomic mass of a certain element by the percentages of abundance for different masses, different isotopes of each element. So to give an example, here, let me just break this off. To give an example, if you have like Cl35 and Cl37, and this one is 75.76% abundance. This one is 24.24% abundance. To find the average atomic mass, you multiply, because these are percentages, you multiply the percent by the mass plus the percent, plus the percent by the mass. So this goes here, and then this goes here. This should make sense, right? You multiply the percent of the entire average times the mass, and then you add all of these percents, all of these fractions up, and you get what the average is, which is 35.45 AMU. That's how they get whatever is on the periodic table, because whatever is on the periodic table isn't a set amount. It's an average of all the different isotopes of the element itself. And this leads to the mass spectroscopy, which can I clear this up? Let me just zoom in a little bit. That's funny. Okay. Yeah, I'll just zoom in. I'll just use that. This leads into mass spectroscopy, which is how they find the relative abundances of each element. Now, I'm not going to draw a mass spectrometer out, so I'm just gonna search a picture up. Give me a second. I should have done this earlier, but let's find one. All right. I just pulled one off of the internet. So let's look at this one. Oh. No. All right, let's just look at this one, right? So what's going on in this, right, is, let's take a look. All right, so basically what's going on, you enter the whatever sample you're trying to find out into this little hole right here, and then you're basically vaporizing it. You're sending a lot of heat into it. It'll vaporize, and then the ions are being accelerated, and there's a magnet here that basically bends the trajectory of the ions, and because they are different masses, the heavier ions are deflected less. Basically what's going on is they're going to bend less because they're heavier. The smaller ones are going to bend more, and this detector here is measuring where they're landing to find the different types of or the different masses and their abundances. So basically the magnet here is just bending different masses of the same element based on its trajectory. That's basically all you need to know about that. And then it'll come out with a graph. It'll come out with a graph, or a table, I should say. And a table here, it'll look something like this, where this would be the percentages and this will be the masses. And this is just calculated the same way as what we did up here with relative abundances. You just read it off the graph and then calculate it. And then with that, whatever average atomic mass you get from this percentage graph, you can find which element it correlates to, which is a pretty common question in the AP course. So that's pretty much good for 1.1 and 1.2. We'll probably start off with 1.3 next. All right, thank you for watching.